All right.
So excited. What did you have to teach us today?
Differentiation.
Is this 9G?
Yep, I believe so.
So exponentials, right? So that is 9G.
Yep.
It's the exact same.
Yeah, but you look at it.
Oh, actually, one opens the fuel cap and the other one won't open the top. So this opens the fuel cap.
All right, the derivative of e to the x. So if you are desperately in need of an explanation, your textbook.
Well, it smells like weird.
It smells like 2-minute noodles.
It smells like too much noodles and gravy and shit.
Let's go
right now.
All right. So
Really?
there's an explanation of this on those 2 pages. If you are interested, you can have a look at
Is
that.
it just like a really long explanation?
It is a really long explanation, so that's why I'm not going to go through it. Because in the end, what we need to do is we need to know the pattern.
So would you suggest writing the explanation in our summary book?
No.
Or no?
You would never need it.
You summarize me like 3 chapters.
Just in case you want to look over it.
Well, I've done. It's like exponentially long.
Wait, so now is this just,
Yeah.
And they're all like,
They're all like the same thing.
is this the pattern?
Yes.
you just like.
So e to the x, when you differentiate it, it's just e to the x. And e to the kx. It's k e to the kx. Alright, so they're patterns that
What's the difference between this civilian and the
exist between those.
Ethan. Shut up.
It's just not pleasant in here. I can't do this.
So, some examples.
And then maximum fresh air.
Be
Oh, but it's
Oh, closing in there. Once I
What
can't-
do you do it? I don't want to.
Nothing. I was practicing
not
in the
going-
music rooms actually.
It's actually like warm in here.
It is warming here.
It's not. See,
Oh,
it's
you
not
got jumper.
jacket.
It's not that cold outside. If you put your jumper on, it is nice outside.
No, it's not.
No, it's not.
It's
It's
not
like
because I can
12 today.
Yeah, I can touch
12 degrees, bro.
This is like the Scottish summer. You guys should toughen up.
Oh, we're sorry.
We
We're
don't live
So, yeah,
in
it should
Scotland
be.
though.
I'm waiting.
I'm
I'm
telling you
pushing
that.
it.
I have the heat on all the time. So it's winter and I'm still sweating in my bed.
Same.
Yeah, I'm like, can we turn the heater off?
Alright. So I've got a couple of examples. So the first example is e to the kx. K is minus 2, so following the pattern, that coefficient at the front of the 2x comes down out the front. So minus 2 e to the minus 2x. Alright, so the power on the e to the x does not change. Now this one here, we need to rewrite the 1/1 as index form. And when it's index form, it's e to the -3, yeah. Alright, and then we just, same process as we did there. So the k comes down the front. -3, and the rest then stays the same. So you get that.
Nice observation.
My observational skills are at their peak.
Now, of course, methods is far more fun than that.
I love it when you make me want to die. You know about the example.
Is that a plus?
That's supposed to be a plus, yes.
I was there. Yes, I did. I had to sit
Ruby, shut up. I'm kidding, I love you.
Why do you never have class?
you're such a good
Are you trying to give back his beanie?
All right, so in this one here,
Liza, shut up.
y equals e to the power of, it's x squared plus 4x, so it's different to these two. In like these were just x there and kx here. This has got a function up there. So if we've got a function within another function, we need to use the chain rule. All right, so we need the chain rule here.
So you make function equal u.
Yes.
I appreciate your validation.
So the bit that's up here as our power there, that function, we make that equal u. So we let u equal x squared plus 4x. So y then is e to the u.
There's a stop, Randy. I have netball. Oh, netball doors.
All right.
I haven't finished. I haven't finished the first example.
Good job.
Wait, I know what nice I can do that.
The u dx, when we differentiate that, what do we get?
Do that.
Sometimes.
You had.
X plus 4. Well, and when we differentiate this one, we get
I can't see.
y to u is just e to the u. So that bit doesn't change. So dy dx then equals those two things multiplied together.
You need a substitute.
And we need to substitute, yes, back our u. So you write it like that, you're probably more likely to see it written like this. So there's a little bit of a pattern here. So because this bit out the front is just the derivative of our power. So note the pattern. The pattern is this. For h of x equaling e to the power of some function, when we, so e to the power of some function, when we differentiate, we end up with this e to that function bit still, and then out the front we end up with
The functioning bit still.
the derivative of the functiony bit. Nearly. So we still end up with the e to the fx part, and out the front it's multiplied by the derivative of that fx. Alright, so that's a pattern. Some people like to use that. Up to you whether you do or you don't. All right, another example.
I just said,
Remember, I got mocked for like at least a minute and a half for making the observation that it was raining.
Oh, was that what, I didn't hear what you said. I was just like,
no, I didn't. Yeah, Jen mocked it.
It was Jed, it was Jed.
I was gonna say.
Yeah, mocked it, and I'm like, oh yeah.
It is something.
What is that? Oh,
Right? Apparently.
Just so I can walk upstairs.
I'll go upstairs and I can carry your blanket.
I can walk upstairs with you like that. It'll be the
Oh,
You'll
don't.
tell me what.
It's alright, I'll go with someone else.
Yeah, leave that.
I do it. How do you do?
Mrs. Sinner,
Yes, Samara.
why does the derivative stay the same for in the paradox or in the paradigm and that sort of stuff?
Good question.
All right, so remember it's about the gradient. So if e to the x is like this, and so the derivative, of course, is the gradient, and at different places the gradient is changes and gets bigger, and it just so happens that here the gradient is at the y-intercept, the gradient is 1. So the gradient is changing in the same fashion as e to the x. No, that's not a great explanation, but that's about the shortest one I can.
Can I assume that the gradient is either the paradigm?
Yeah,
Okay, ready?
that's the pattern that turns out with that. I could do, you know, the first principles. We could go and do the big first principles thing, and that will take a long time. And so yes, the gradient changes the same as the e to x changes.
Okay, thank you.
All right, so the gradient of the curve. So what the gradient is the gradient's the gradient. Very good.
It's dy
Oh.
dx.
dy dx, thank you. Right, remember, gradient, dy dx. It's very important that you don't forget that. That's what dy dx, yes, it's the derivative of the function, but also tells us about the gradient of the function. So dy dx on this particular one is what?
E to the 2x.
Where do you want me to put the 2, Lara?
In up the top, maybe. And behind E.
And down the bottom, right?
Oh,
Somewhere at the
okay.
equation.
And,
And an X up there.
Up there.
Yeah, cool.
right, so there it is. We want to know it at this point here. So how do we find it at this point here?
You substitute the 1 in for
You
x.
substitute the 1 in for x. This has an x, so the gradient there, which is dy dx, equals 2e to the 2 times 1, 2. And leave it like that.
I have a question.
Yes.
Why does the 2, the power of 2x stay there? Like the limit of 10x.
Because it doesn't.
Doesn't do that for exponential.
It's
Well,
a
yeah.
rule.
Where did the X go?
Yeah, Mr. Sinner. Jeez.
Can we just establish that?
Think times
You're going to
by
put in the
1.
1 and then you get that X. Oh, cool point.
Maybe write substitute 1 in or something.
I'm so dumb. I got it.
Mega brains.
They'll come one day.
Subscribe to this.
Oh.
Yes.
Thank you. Oh, I've even written that down. Yeah.
It should all come as minimal.
All right, next one. Right, we're doing 2 exercises today because we're a little bit behind and there's people away tomorrow, so
Is that the end?
no.
We're doing another.
No.
You just said we have another example, and you're like, is that it?
Oh, sorry.
Right.
Not another example.
Am I rubbing this off?
Area
Back
with
with
the
You're rubbing this off.
today.
logarithms, right?
Logarithms.
These ones are actually easy though.
So we're doing 9H now.
Yeah.
I'm like, focus on 3 chapters higher because they're all the same.
It's okay.
It's 9H. It's 9H.
All right, there's a proof.
You don't need the proof, it's okay.
If you want the proof,
I believe you, Mr. Sanders.
have a look at it. Page 386. However, the real rough proof is this. So remembering that this is the gradient, so the derivative is the gradient. So here the gradient's really big, positive. Here the gradient's,
You're getting closer to 0.
you're getting closer to 0. Here it's getting still closer to 0. And so when we join those up, that curves around like that. What does that look like? No, I don't need the x function. What about if I put another bit down in here?
Looks like a reflection.
Hyperbola. It looks like a bit of a hyperbola, doesn't it? And so that's in fact what that is. It's a part of a hyperbola. Now it has a restricted domain, of course, because the domain can only, we don't get this part of the hyperbola because we're only looking at positive x values, because we can't take the log of negative numbers. All right, so that's where this first bit comes for the function. It's for r positive, so it's only the positive x values that correspond to this black curve. All right, so there's a domain restriction there for log. So log base e, kx, where k is greater than 0. Then the derivative, and the derivative, of course, has to be in the same domain. We can't all of a sudden, we can't start with this and then end up with something over here.
Is that KX
In there.
Is that KX or power 2? Or is it just normal?
It's just in the bracket normal, it's no power. No. So f dashed x looks like your hyperbola, which is 1 on x. Now there's no k in it, and the reason there's no k in it is when you actually do this differentiation, you end up with a k on the top and a k on the bottom, and they cancel each other out.
So whatever that x is, it's going to go under the 1. Does that make
Whatever
sense?
that x is going to go on the 1.
What did you say about the cancel out then?
If we were to do this and do it by longhand,
Yeah.
what you end up with is a k on the top and a k on the bottom, and they cancel. So that's why it ends up as 1 over x.
So the K1 and KX.
K1 and kx, and the k's cancel. All right.
Imagine walking around with a speaker on a strap over your shoulder. And it's
So much evidence.
Imagine having nuts that big.
Yeah.
Just how much of a stand-up guy you have to be.
Imagine how
Good of a
still be a
person
cocky.
you are.
Pardon?
You don't have to be a stand-up guy, you can just be a cocky.
That's the joke.
That's what I meant.
Camera's on there, Zeke.
Yeah, it's only Cameron.
Oh, the camera's on there.
No, but Cameron's gonna listen to it because he missed the message.
Oh,
So it's going to be all over YouTube because I'm so popular.
Cameron's not good.
There's going to be millions of people across the world.
Okay,
Did you know
like
it just surpassed 100 million
He
bet you.
Terrible, isn't it?
Why is wearing his nice shirt?
I better put a reminder at the end of this one.
Yeah. I'll stand in front of the camera and say like and
Or
subscribe.
like
please.
these discussion page notes.
Oh, did you see there's this thing in the
So we're
news?
gonna hear
It was
probably
like
about how he's.
tradie becomes social media
Yeah,
influencer
definitely hear
to
about.
prove to his daughter that it's hard.
It.
And he's got like
All right.
400,000
So with these here, you notice I've got these domain restrictions here because remember, log, we can't take log of negative numbers. So these domain restrictions keep this bit inside the bracket there as positive numbers. All right, first one's pretty simple. dy dx.
It's just whoever, right?
1.
1 over x is what it is. All right, next bit. All right, so what's different here with this one? It's got a +3. So if it's got a +3 on the end, means we've got not just an x or a kx, but we've got some function there. So if we've got some function there, it means we need to use the chain rule. Yes. So in the chain rule, u is going to be equal to
5x
5x plus 3, and then y will be log to the base e of u. All right, differentiate 5u, 5x I should say.
5.
You get 5.
What's 5x plus 3? Sort of.
And differentiate dy du, that would be 1 on u. So when we put those together, by multiplying and substituting the u in there, we get that, which is 5 over 5x plus 3. So you can see in this case, we've got the +3, but you can see this coefficient ends up on the top and on the bottom. But because we've got the +3 there, we can't cancel them out. But if we did the same thing here, we'd end up with a 3 that we could cancel. All right. Right, there's a pattern there on that. And so I'll just highlight that. Sometimes it can be useful. So if we've got y equals log to the base e of ax plus b.
You're right, Amara.
Questioning my life decisions.
You always break up with
It's never an option.
Maybe after winter when she doesn't need body warmth.
Don't take a budget.
But why?
All right, so the pattern is that. So if you've got just something ax plus b, pattern you end up with your a on the top and this function here on the bottom, which is what we found here. 5x plus 3, the 5 is the a, we've got the 5 on the top and the x plus 3 on the bottom. Again, some people like that. All right. And it's the same with any other art.
Don't roll the top bit. Is that it?
I'm going to do one more example.
No, you said that one more example ago.
Ah, well,
I think you said 2 examples ago.
I can't count very well.
I thought you were just going. It's Antica. Was that you, Ali? Oh, poor Aaron. I don't think that's so
What do you think someone with cat thinks? Someone's just gonna go,
All right.
and then Geordie J.
maybe they're me.
What was you using?
Use the chain rule.
So we've got log to base E of x all squared. Any ideas?
Chain rule.
Chain rule. Good, because we've got a function, log e to the x inside another one, which is x squared, so chain rule. All right, so in this case, u is log to the base of e of x, and y equals u squared. So du dx is
1 over X.
1 over x, and dy du is
2U.
2u. So we now need to multiply those things together. So it's 1 over x times by 2, and replacing the u by log to the base e of x. We end up with that.
Why can't you cancel out the X?
Right, you can't cancel out the x's because this
That's
is all
connected.
together, and that's log to the base e of x.
So basically the log
If
is.
it was the.
It's not log e times by x, it's log to the base e of x.
Was that truly the last one?
Truly, the last one. So that's 9g and h. Alright, so the rest of today and then tomorrow as well. And don't forget to like and subscribe.
Yeah. Now you have to wave the
So I want
camera.
to listen back to one of those.
Bye,
interviews. Bunch of idiots.